Okay, let's get started. This is going to be hopefully a nice, just interesting lecture, trying to stimulate you. There you go. We'll look at sort of some experimental techniques in the area of condensed matter physics, just some, not, of course, there's huge numbers. So this one is going to be a little bit talking about computation in physics. And there was this very interesting article in Physics Today some time ago, computing in physics, are we taking it too seriously or not seriously enough? And it's fair to say that computing in the area of physics has grown hugely over the last 10 or 15, 20 years. So you can really calculate very many properties of materials nowadays and very accurately. So I want to just show you, firstly, what's the most widely used and successful method of doing that, and give you a feel of what kind of properties and materials can be studied. Okay, in the course you have learned about electronic structure, the band structure and density of states of materials, a little bit about magnetism and phonons. The electronic structure of material is really responsible for all of its properties. So it's a really very, very important aspect. From the electronic structure, you get the structural properties, the atomic positions, and whether or not a material is stable, metastable, or unstable. You can calculate dopants in various materials. You can predict phase transitions. You can investigate also the ferroelectricity of particular materials. We calculate here the carrier mobility of semiconductors. We did a bit of that before. Density of states, band structures. We looked at some magnetic properties, and in terms of permanent magnets. But you can also dope semiconductors with magnetic ions and turn semiconductors into what we call dilute magnetic semiconductors, which are sort of used in spintronics applications, which is a big emerging field. It's written here, spintronics and multiferroics. Multiferroics is where you have, for example, magnetism at the same time as being a ferroelectric. And superconductivity. Nowadays we can study and calculate and predict superconducting transition temperatures. If I get time, I'll show you an example of that. Once we have the electronic structure, we can calculate the total energy of the system, and we can calculate mechanical properties, stress, strain relationships, bulk modulus, elastic constants, and so on. And of course, once we know the electronic structure, and if we can couple excited state theory to that, which we can nowadays, you can accurately predict optical transitions, predict experimental optical absorption spectra, and so on. So it's a very important aspect of your material. Okay, so I'm not going to delve too much into the equations. We're going to be looking at density functional theory. So, but as I said, I'm not going to go into the equations. I'm more interested in showing you applications of that. What I will do, because there's many very good textbooks out there, there is this very nice article that talks about this approach, and it doesn't have one equation in, so it's very wordy, and it gives you a good feel of what it's about. And of course, there's very many textbooks on it as well. But this is really nice in that it gives you sort of an understanding really easily of what it's about. So, the Hamiltonian for your system here, we consider just the electrons here. You have the kinetic energy term, which you've seen many times before. Okay, this h bar squared over 2m, your operator. And here you have to take into account the potential. Okay, so this term here describes electrons at position R interacting with all the ions, the atoms in your system. And then we have the interactions between the electrons. Okay, and this is a hugely complicated thing which we need to make approximations for. So due to Walter Kohn, he developed this theory where basically he calculates the total energy of your electron system with your atoms, your material system, your condensed matter system, not as a function of the wave function of the electrons in your system, but as a function of the electron density. Okay? So you can imagine this electron density, it just tells how many electrons there are at any point x, y, z in your crystal. So the density is just a function of 3 variables. The wave function, on the other hand, you can imagine how many electrons you've got in your system, how many atoms you've got. This is an extremely difficult thing to solve. So he replaced this wave function by the electron density, and he derived a set of non-interacting single particle equations. So it was like each electron was interacting with, it's okay, not each other individually, but just interacting with the potential that is created by the other electrons. Okay? So, yeah, he got the Nobel Prize for that in 1998. So, very important work. And at the end of it, the total energy of a system, which is called E0, if it was expressed as a function of the real wave function or as a function of the electron density, they are exactly equal. And he has proved that's exactly equal. And so this is an exact theory, which is great, but there is one difficult aspect of this theory, which I'll just mention briefly. Okay. The difficult aspect of this theory is something called the electron exchange and correlation potential. This is not known exactly, okay? So this is the only part that is not known. That is like if you change places with your electrons, how does that change the effect of the potential in the neighborhood? And various approximations are made to describe this. There are many, many, many different sorts of approximations. The very first one was called the local density approximation, and then there was a slightly improved GGA, meta-GGA, hybrids, and so on. Presently, I'll tell you the current state, most people nowadays use a GGA, which is slightly improved over the LDA, because the LDA, well, let's say the GGA takes into account, if you're an electron and you feel the potential going upwards, the GGA describes that gradient of the potential, like going upwards. The LDA just says, what's the value here? Okay. Hybrid functionals are really very, very good state of the art, various sorts again, but if you're doing a calculation, it may take you 100 times longer than the GGA. So a lot of people will calculate large systems using the GGA, and if you need accurate calculations, in particular for band gap values, like semiconductor band gaps and optical transition defect levels, then you will, nowadays, people expect you to use accurate hybrids. Former days, you could still use this and make some statement or estimate how, because DFT within the LDA or GGA underestimates the band gaps of semiconductors, and that's well known and understood why. Okay, but these new functionals allow very accurate band gaps. So a little bit about what you do. most of these calculations, if you have a small system, you may be able to do it on your small cluster or possibly even your laptop. But if you do larger systems, you will need some kind of computer cluster or even the NCI supercomputer in Canberra. Most groups in Australia run on the NCI supercomputer. So it's an iterative scheme. You start off with some guess for your distribution, your electron charge distribution. So you might just assume that your starting density is a sum of the densities of the atoms. And then you will make some guess for your exchange correlation potential and add that in here to your Hamiltonian. Diagonalize the eigenvalue matrix. You'll get your eigenvalues and eigenvectors, where the eigenvalues can be thought of as wave functions of your system, but the eigenvectors values will be the energy levels of all your electrons in the system. And then once you have these, you will recreate the wave function here as a sum over coefficients and orbitals. Then you'll calculate again. You made a guess, you've calculated the wave function, and then you will put that back together, calculate the new density, and you will iterate and iterate until the density that goes in here doesn't change to the density that goes out. And that may take you like 100 loops of the calculation. Sometimes you'll swear because it won't converge. Sometimes the calculations are difficult to converge, but usually they do. And then once you have finished this, you will have the ground state electron density, and therefore the ground state energy. I probably should just qualify that. You have to assume some position for your atoms, okay? So that is assuming you have input the position of your atoms, then you can get the corresponding total energy and electron density. But if your atoms are not at the ground state, if they are experiencing a force, then there is another loop, like outside of this loop. If you want to relax your atoms, you can. You say, calculate the force on the atom, and if there's a force in that direction, you take a small step that way to reduce the force. You recalculate the electron density again, and calculate the force again. If there's still a force, you keep moving the atom, until it's at its until the forces are below a threshold. Okay. So with this approach, you can relax the position of the geometry of your materials. Having said that, it only works in a potential. Okay. So if you are at a local minimum here, but it's a potential, the total energy goes upwards, and the real structure's down here, such an iterative procedure won't allow you to jump over that barrier. Okay, it can roll down hills, but you can't jump over barrier. There's another approach that you need to do for that. Okay, so people, as I said, run on this computing center at NCI, Raysian. Has anybody had experience running on that? Maybe you've had some other little projects, like special studies project or something? Yeah, it's a very big machine. It's got 84,000 computing cores, and each core has several number of CPUs in it. So it's a really powerful one, and the codes are all parallelized so that you make high efficiency of your calculations, and they can run faster. For example, if your wave function, in these kind of approaches, there are various ways you can expand your wave functions. Some codes use plane waves, simple plane waves, okay? So you might have your wave function being expanded in like 10,000 plane waves or something like that. And so the plane waves can be distributed on different cores and calculated at the same time. That's one way of parallelizing the codes. Okay, So a little bit again, what do we input and what do we output in general? Okay, we input the structure of the material. We have to tell the system where the atoms are. What we get out, as I said before, is the electronic structure. You've met this before: density of states, band structure, effective mass, electron charge distribution. We didn't talk about that, but you can get that out. If you have the density of states, then you can plot out the density on each atom that you want. And magnetism. These codes can also do spin polarized. Instead of just dealing with one density, you can say, I want to do spin polarized, so I treat the electron density of the up electrons and the density of the down electrons separately throughout the whole calculation. And yes, you can do spin polarized calculations and obtain the magnetism of your system. Yeah, we also get out the total energy. Okay, so this allows us to get the structure, the atomic structure, as I said before, by calculating the forces on your atoms. You can minimize those forces by shifting the atoms, and you will then end up at the ground state geometry of your material that it wants to be in. You can also calculate the atomic vibrations, as you know, phonons. We did the linear chain, but you can imagine that's done in 3 dimensions, and you can get your 3-dimensional phonon distributions. Elastic constants, well, I don't think we calculated that, but if you have the total energy, you can calculate elastic constants through, for example, the derivative or second derivative, I've forgotten, of the potential energy versus lattice constant curve. Okay, then there's various, you don't just get the total energy. The total energy is normally at temperature 0, but you can also get out the internal energy, the enthalpy. There is a temperature that goes into the calculations, a small temperature. So normally it outputs T equals 0 results and elevated temperatures. But the thing is, unless you're doing a phonon calculation, the temperature that you put in acts more just as a smearing of that Fermi function. Remember, the Fermi function at T equals 0 was, for a metal, a sharp step function. In the calculations, that can sometimes cause trouble, so sometimes you smear that out a little bit, and it helps to converge in this iterative cycle. And then you have to extrapolate back to 0 what you have done to your result. That's more of a technical thing that I shouldn't bother even actually mentioning. Never mind. Okay, and from the band structure, you can calculate various optical properties. Okay, and you can compare with experiment and so on. So where does this kind of approach sit? I think it sits kind of in the middle here, right? You have pure theory, pure equations where you derive, fundamental laws and things like that. And over here you have, experiment where you're actually doing experiments. In the middle here, you can think of the computation, and it's also combined with a bit of intuition. For example, you have to guess which structures might be relevant sometimes. And this way we can put these two together and learn something new. Often you need, I guess, everything to understand something completely. Okay, people talk today a lot about multi-scale modelling, right? This kind of picture typically is shown here. You have the electronic structure, what we have been dealing with, right down here on the terms of atoms, the electronic structure, the atomic positions, and so on. And this is largely the domain of physics, I guess, down on the scale of nanometers, even angstroms, right? Over here we have engineering, material science, and chemistry. They're all sort of related and intermixed here. And what you can do is you can link your microscopic atomic information to more microstructures, if you kind of, for example, use a statistical mechanical framework, you can go from a very small atomic level, up to larger scale. For example, you might use kinetic Monte Carlo, or kinetic Monte Carlo, like you will calculate. I guess you're familiar with Monte Carlo schemes. That's a statistical mechanical scheme, right? You run it for a long time. You have lots of different moves, but the way the atoms interact with each other, you get those energies, from the calculation. So you can input from the atomic level accurate calculations, input those numbers into more statistical mechanical framework that can describe things on larger scales. There's lots of those kind of calculations in the literature. Okay, this is what I kind of wanted to show. Recent 1990, you can see something happened here at 1990, and that's basically when Walter Kohn and all of the guys there started developing this theory, and also the computer codes around them. And the number of publications has thereafter exponentially increased. And it's interesting to notice that the top 10 papers in the physical review journals, including PRL and PRB, they're all DFT papers. Okay? So it's a huge field. It may be small in Australia, but it's huge elsewhere. Relatively small in Australia. Okay, so let's just have a look at some examples here. Okay, everybody hears that Moore's law is nearing its end. Okay, that's the reason we are looking at, quantum computing and nanoscale and everything. So what does it say? It's not really a law, it's just something that has been observed over a period of years. For example, okay, here we have a plot. Hang on, what have we got here? Number of transistors fitting on your chip has doubled about every 2 years. Okay, that's fine. The numbers of transistors on a chip, you can see, is still going up. 2016, it's still going up. What's not going up is the clock speeds. Since 2004, it's been flat. Okay, and so it's limited. The clock speed is limited mainly due to heat. Okay, so new technology is needed for increased power. No, so we need something cheaper and faster that creates less heat. So alternative materials and mechanisms are being pursued. Yeah, and this just shows, it's interesting to see that about every 10 years, some different kind of computer has been developed. Okay? Smartphones, embedded processors, who knows what's going to come down here. Okay, so one area that people are looking at is so-called molecular electronics, or Moletronics as they call it. What you have here is you're creating some kind of device. Here you have the electrodes, some material, and this is the functioning device here, which is some kind of, well, I guess it's some kind of molecule, okay? And so the idea is that, one, it's extremely small, and you've got a lot of control over exactly, what the thing is doing, provided the experiments can actually control down on that scale enough. And more they're being able to do that. What's also good is for the theory, finally experiments are coming down and getting accurate enough so that these kind of calculations are easily doable. Okay? Before, when the devices were so big and had so many defects, often theory did not one, it couldn't calculate such a big chunk of material, and two, often, I mean, it's still a problem. If you collaborate with experimentalists and experimentalists with computer people, often the experimentalists sometimes don't know all of the things they've got in their material, right? So they might have some kind of impurities or defects, right? And if you don't incorporate those impurities or defects, then you're going to calculate something that's not what they are observing, right? So this is a study, for example, looking at such a molecule and trying to investigate a switch, on-off switch, using what's called tautomerization. So what is that? These little blue spheres are hydrogen atoms. So the idea is that in a particular state, you may allow conduction through your molecule, and if you have control and are able to switch the position of this hydrogen atom to be bonded to this atom here, and the same over here, this one has now gone over to this one, does that change the conductivity of your device? So you can calculate that by creating some electrodes. In this case, it's just a chain of carbon atoms. And then using the theory, you can calculate using density functional theory, coupled together with a non-equilibrium Green's function approach, you can calculate the quantum electron transport through that device. Okay? These are some equations. I'm not going to go into explaining them. They were developed in these publications here. But what you can see is this is the current through the device as a function of bias voltage. And if you look at the first configuration, you can see, as you might expect, the current just increases as you go from, say, about -2 up to 2. But when you investigate or calculate the current voltage characteristics for the other state of the molecule, what happens is you get this dotted curve here. So you get no current. So, and there is also a metastable state where just one of the hydrogens change position onto this atom here, and you get a result sort of halfway in between. Okay? So if you are able to control, switch perhaps with an electric current, the position of these hydrogen atoms, then you'll be able to switch this, be like a switch on and off. And many electronic devices need these kind of switches. Okay, so that's one example. And then, you know, you can, with the calculations, you can go down and say, well, why is that happening? And you can investigate, you know, the actual orbitals that are controlling the current. You can investigate the transmission matrix and see where you get, for example, this dashed curve corresponds to the off state, and it's very close to the Fermi level, and it's a minimum, so it clearly coincides with very little current. So this is the off state. When you look at the eigenstates, if you like, of your device, what you can see is that there is, this is the anode, or the electrodes here. There is no coupling of the orbital of the molecule to the electrode, whereas in the on state, it does, it couples. So you can understand that electrons are able to hop from one electrode right through to the other. So you can pull to pieces your results and analyze them and understand them. Okay, I will just show briefly. This is a kind of similar study, but instead using a diamondoid, which is a small diamond particle. In this case, it's suspended through electrodes that are gold via, again, a chain of carbon atoms. Cumulene, it's called. And I won't spend too much long because I think I've explained, sort of given a good enough example for that kind of calculation. But what was found in this case is oscillatory behavior depending on the number of cumulene atoms, for example, and rectification. So it functions like a rectifier. So in the negative bias direction, you are not getting any current through. In the positive direction, you are getting current through. A small current for the even numbers of cumulene atoms, and a large current and a negative differential resistance, which means this peak doesn't keep going up, it's bending over. So really some very varied and interesting behavior in these kind of systems. Again, as I said before, you can pull apart and analyze where it's coming from, and you can even locate on your particle which atoms are responsible for the rectification behavior and which atoms are responsible for the nonlinear differential resistance and rectification behavior. They're color-coded, so you can plot these curves for each atom. For example, the green is on this layer of diamond atoms, the blue is for this result, and so on. So you can analyze what is responsible. And so if you're able to identify which atoms are responsible for which characteristics, then that opens up for you to be able to change that behavior if you don't like it, or it may also show you how to induce that behavior in a different system. For example, if you would come in and functionalize it with a different atomic species on these atoms, then you may eliminate, say, the rectification behavior if that's what you desire. I don't want to, just the final one on this kind of thing here. As I said, devices, they need a whole lot of new kind of functions and materials. In this situation, this particular molecule functions as a spin filter, okay? So for spintronics, which is where we want to be able to control both the spin of the electron and the charge of the electron in the same material, we are going to need spin polarized electrons. And we're going to need materials to be able to create spin polarized electrons. So, for example, here, if you calculate the current going through this particular molecule, doing a spin polarized calculation now, what you find as a function of bias voltage, the current through the alpha spin up is significant, and the current passing through in the spin down is 0. So what it means is that you are able to create purely, I think it's almost 100% or 99% spin polarized electrons by running through that junction. There is the density of states up there, which you are now familiar with, which is good. May skip this a little bit. This is turning now to multiferroics, where you have the coexistence of ferroelectric behavior and magnetism. I just want to say that up until fairly recently, it was thought that there were very, very few multiferroic materials that exhibited magnetism and ferroelectricity. However, some new materials have been found which exhibit both ferroelectricity, so you apply electric field and the position of your atom changes, but also it exhibits a crossover behavior. So what does all that mean? Okay, what does that mean? Here the system is cobalt-doped lead titanate. So you are putting a cobalt atom, doping this material with a cobalt atom, and What you're calculating here, for example, is these two calculations show the same thing, but they're calculated just with different methods. Often people have to calculate with two methods. As I said before, you might do most of your calculations with the GGA because it's cheaper, faster. And then people, and you, will want to know, well, how is its behavior with the most accurate one here? So you just check that it gives the same result. You can see that the barrier height is actually larger with a more accurate approach. Okay, here it's 0.4, here it's 1. But you can see that the qualitative behavior is the same. You have this barrier here between two different spin states, low spin and high spin. So what does that mean? It means that this system is capable of being switched possibly by an external electric field. You know, we're always interested in being able to flip things from one state to the other. So it's possible with external control, you can put the cobalt in this low spin state, has a certain geometry, and the high spin state has slightly more buckled geometry at will. Okay, so it becomes again like a switch. Remember we had here when an atom is in an octahedral arrangement, the d electrons of the transition metal, in this case the cobalt atom, is split into 3 lower energy levels and 2 higher states. The cobalt has 6 electrons, 1, 2, 3, 4, 5, 6, and this is called the low spin state. So you are occupying your electrons here, 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 and then instead of going up here, here, they are going back into the lower state. So there's no net magnetization. There are no, all of these spins are paired, so you get 0 magnetic moment. Okay? On the high spin state, you fill, 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 fill. You've got one more to go. You've got to put it in the lower state. You calculate, count, 1, 2, 3, 4 electrons with spin up, so you have a magnetic moment of 4. That's why it's called a high spin state. 4 is high compared to 0 is low. And again, you can plot the density of states like you're now familiar with. This is for the low spin state with no magnetization. You can see the up electrons are exactly the same as the down electrons. Okay? And over here, for the high spin state, you can clearly see the spin up electrons have quite a different density of states to the spin down electrons. Okay, that just shows there are also other materials that you can dope this oxide with. For example, nickel does the similar kind of thing, and so it's quite a significant finding at the time, which is quite recent actually. Let me see. I'll scan through a little bit here. One can also calculate topological insulating behavior in particular materials. To be a topological insulator, you have to have here the material behaving like an insulator in the bulk, but on the surface it's metallic, and in particular the spins are perpendicular to the momentum, and also at a given energy you have purely spin of one direction and spin of the opposite direction, and it exhibits this characteristic crossing over of the energy of the surface states in the band structure. So this is the band structure. It's called the projected band structure. I didn't show you what that looked like, but if you can imagine your bulk band structure, and if you have a surface, you can somehow project the bulk band structure onto the surface. And then what you see in the gaps are surface states. Okay? So if you would sit here at this momentum, this K value, and this energy eigenvalue, and plot out the wave function of how it would look, and you can do that, you would see that this state would just be all along the top or outside the surface of your material. Anyway, that's the surface band structure. So I'll just skip through here. There's certain materials, you can create them in layers that exhibit topological behavior, and its behavior depends on how many layers you have of these particular materials and how they are aligned with respect to each other. This, for example, shows if you just have one of these layers, I think it's got 3 layers in one layer, you will get a band structure that looks like that. You can see it's clearly just a semiconductor. There's a band gap here, right? If you put 2 of these layers stacked on top of each other, you can see that you're starting. I think there's still a tiny band gap there. These are not got the right behavior yet. But I think when you go to 6 of these layers, then you actually get some topological behavior. And you can investigate these states to verify that they actually do exhibit the topological characteristics. They have to exhibit a change in symmetry as you go from one layer to the next layer between the valence band maximum, the HOMOs, or whatever it's called there, to the LUMOs. Anyway, the final thing I want to talk to you about is kind of an interesting recent study using machine learning to predict materials properties. It's very kind of popular, I think, in all aspects of physics right now. But what you can do is if you can calculate many different, you see, for example, this is a family of semiconductors that could have use as solar absorbers. But to be a useful material, it's got 4 different sorts of elements. So you can imagine it's really many different combinations could be possible of these structures. To be a useful one, it has to have the correct band gap, you know, and it has to be stable. There's no use predicting, oh, this structure is good, it's got the right band structure, but experimentalists go to try and make it, and of course they can't make it, it's not stable. So that's pretty useless. But what you can do is, but by calculating, what you do is you calculate a lot of different possibilities, and then I think we calculated, I've forgotten how many we calculated. But from the few that you calculate, what you create is so-called descriptors that describe certain characteristics of the atoms that you've got. And then you run your particular machine learning code, and you can predict, you can ask which of these materials, it scans over lots of thousands of different possibilities, and you can pull out or predict which ones will have the band gap in the right order of magnitude. And for example, it was found 717 of the possible combinations, I think it's 1,568, had a band gap in the sort of range of 0.5 to 2.5. So they could be potential solar absorbers, but they may not be stable yet. Okay, so the first step. And with the optimum range, there were 242, the optimum range being 1.2 to 1.8. And then of these 242, you can look into, there's a materials genome, and that's got millions of different structures in it, and you can search and see which of the structures are stable or metastable. So of all of these that were looked at, 34 are potentially of interest and unexplored so far. So that's the upshot. So this is a table showing, people usually don't just use one method. There's a lot of machine learning algorithms out there. 1, 2, 3, 4, 5, 6 were tried, and then you have ways of characterizing which scheme has a good probability of prediction, and so on. And, okay, these are just plots that were made of the structures, okay. Oxides were tried, sulfides, selenides, tellurides, and this is a plot of the band gap. So you kind of get the idea. If you look at the oxides, you can see the band gap of the tested structures spanned quite a long way, even to negative band gap, which is possible. Just means your conduction bands overlapped with your valence band and no band gap. Most of them had a band gap around about, what is it, 4 point something. And on the other extreme, you can see that the tellurides had a smaller distribution of band gaps, and in general, the predicted band gap of most of the materials was down here at 2, less than the oxides. Okay. So that just lists all of the predicted structures. Those are the ones that are of interest. And as usual, nowadays you have to, in a paper, you have to supply so much supplementary data. I know one colleague of mine, he submitted 250 pages of supplementary information. My God. So, who wants to read all that? But, you know, some people, if they want to try and reproduce somebody's result, then they will really want to see the details. And I guess it also gives validation that the person is doing the right thing with their, you can see what they've done exactly. The other machine learning application that we have done is with layered materials, okay? We're not the only people, a lot of people are looking at these kind of things right now. So in this case, on the basis of, I think, of the order of hundreds of structures we actually calculated. So the idea, these kind of systems are really currently being considered for devices, okay? So, you know, it's graphene forever, right? And then you know, other single layers like boron, nitride. But now people are starting to like put these layers together and see how the properties are different, 2 layers or 3 layers or whatever, of different freestanding structures. Yeah, it's quite exciting because the experimentalists can now, you know, control a lot of these 2-dimensional structures. Some still have to be supported on a substrate, however. Anyway, so what the point is, we want to be able to predict what is the band gap and what is the lattice constant and what is the interlayer spacing for many combinations of these structures. So again, you get your data by doing very many standard calculations on your computer, and then you use machine learning and you create your descriptors as input, and then the code runs and you can predict particular combinations of layers, and you can predict the interlay spacing and the other properties that I mentioned. So of all those systems, some of them are listed here. What is plotted? The name, of course, gives you which system was considered. Okay, you can see here graphene, zinc oxide, and so on and so on. And this tells you how many of those materials were involved in the search. Okay, let's just give you a feel of the numbers. And then, you know, you can analyze your results in a particular way, and you can see the predicted versus the real by how close the scatter is to the lines. You can see there is some scatter. I think this is the best algorithm. In this case, we had feed-forward neural network, random forest, vector machine, support vector machine. We tried 4 different ones in this study. They all kind of predicted very, very similar results, I think. There's some deviations, as you would expect. Yeah, and so that's where our study ended, but just looking at the 2 bilayers. But you can imagine that, we can look at even more now. You've got it built up. You can look at 3 different layers, and as you can imagine, it quickly becomes very impossible to do that by straightforward calculation, direct calculation with DFT. But these machine learning algorithms, can be very useful for searches, material searches. Okay, I think I'll leave it there. As I said before, next lecture, I'm going to get the old exams and just give you some idea of how the new exam will look. I mean, it'll be very similar to the old exam, but I'm going to show you, like, some people may think, oh, this question, we didn't do that. Should I know it or not? I'll put a big cross and say, no, you don't need to know it, and stuff like that. All right? So I think I'll leave it there. Yeah, don't forget the quiz, number 3. 10 o'clock will be gone over with you if you probably haven't managed to do it, I guess, because it's a lot all at once. Yeah, that's it.
Just had a question about the assignment.
Yeah, sure. I've got it all here. Hey, let me just untangle. Which number?
5B in particular,
Yep.
I think I.
Yep. This one, 5B. 5, which one? This one?
Yeah.
Okay. So what are we doing? We're applying a field to the magnet. We've given the saturation magnetization, which is, you can essentially say when all of the...
Yeah, I was basically wondering, do you just use those?
Yeah.
Oh, okay. But yeah, I was a bit confused about how you find the actual percentage.
Yeah. So what you can, this is your expression here for the magnetic field inside the thing. It's going to have that, and it's going to have its magnetization, right? So you are given... so you're given the total, right?
Yeah.
So you're given so you'll get something like that, okay? You can obtain the magnetization. Okay, so that's the first step. But then you say, oh, how do I get a percentage from here, right?
Yeah.
So you can assume that that is saturation magnetization, they're all magnetized.
Yeah.
And so it's just a percentage of this from that.
Oh, so
Yeah.
Okay, that's actually a lot easier.
Yeah, that's easy.
Thank you.
I'm just wondering, with some of the molecular gates, I guess you call them, are they actually experimentally proven, or is it all theoretical at this stage?
No. There are experimentalists working it out. Probably a lot more. I mean, it's so much easier for full calculations to experiment. But yeah, there are people.
And nothing published yet?
Oh no, there's always
Yes.
people also actually in other countries see from the electrical engineering department also have they are doing research on little devices like that. Electrical engineering, you kind of think they're doing some electrical stuff, but they're actually doing some devices.
And so can you apply, I saw one of the papers in that top 10 was for like a non-homogeneous gas. Can you apply those sort of models to like atmospheric gases or pressurized gases?
You might be able to. That's kind of getting a little bit out of my expertise.
Yeah, it's kind of heading more towards like plasma sort of
Yeah.
physics.
Are you coming from plasma?
I'm thinking about doing something